The 2025 Physics Nobel Prize has been awarded to macroscopic quantum tunneling. I don't know anyone who had this on their bingo list. What is this? Why does it matter? And who are the people who won the prize? I have a brief summary. The prize was awarded to John Clark, Michael Devoret, and John Martinez, and it's a case where much of it can be traced back to a single paper that was published in 1985. This paper shows results which demonstrate that macroscopic quantum tunneling is real. Quantum tunneling, you might have heard of, it's a case when a quantum particle can go through a barrier even though it doesn't have enough energy. That is, if the particle didn't have quantum properties, it'd be trapped. But if it has quantum properties, it can leak through the barrier. The probably best known application of quantum tunneling are electron tunneling microscopes. These probe basically the surface of a material atom by atom because electrons can tunnel into the tip of the microscope. However, this is a teeny tiny effect for single electrons. The three who won this year's Nobel Prize figured out that this can also happen for large collections of particles. In particular, they were looking at currents in superconducting wires. This is maybe not exactly your idea of macroscopic. Personally, when I hear macroscopic, I think of a bus. But a current in such a wire consists of millions of electrons, and that's quite large compared to the single electron level. What they showed is that the collective behavior of the current in the wire can tunnel across a barrier, so that's literally a gap. The wire needs to be superconducting for this to happen because otherwise the electrons don't behave as one quantum state. This means that these wires must be cooled to temperatures near absolute zero. You can see in this figure from the Nobel Prize winning paper that as the wire is being cooled, the current behaves in a way that it'd be impossible without quantum effects. The relevance of this effect, and this is why I guess they awarded it a Nobel Prize, is that it moved quantum physics into the microchip range. In the 40 years after their discovery, this insight exploded into a vast number of applications, the best known of which is probably quantum computing. Because once you have this current that can tunnel, you can also have a current that's both on and off. And that makes a qubit. Now, the quantum computers with superconducting circuits, which are being used by Google and IBM and Amazon and so on, don't use exactly the same technology they used in their 1985 experiment, but it goes back to what this group did in the 1980s. The effect is also being used in some experiments to look for dark matter particles that might interrupt the currents. Besides that, I don't think it has yet a lot of applications. I think that the biggest downstream effect of this discovery has been that it made quantum technology a reality. It's still mostly an academic enterprise, but one that's on the way to practical applications. And this has entirely changed physicists' attitude to quantum mechanics. In the 1980s, when these guys did their experiment, quantum physics was a mostly philosophical enterprise. No one thought it'd have much practical relevance one way or another. All this stuff with things being in two places and spooky action was just so far removed from anything tangible. But the macroscopic quantum tunneling was a major turning point that moved quantum physics into the tangible range, at least if you have a physics lab with superconducting wires. Back then, they argued all night over the interpretation of quantum mechanics. Now, they argue all night over the interpretation of quantum mechanics, but in a clean room. So, what are we to make of this year's Nobel Prize? It makes sense that rather than giving a Nobel Prize to quantum computing, they would give a Nobel Prize to the technology that made the first quantum computers possible. Though, as a theoretical physicist, I find it to be somewhat depressing. I, as many others, thought that the Nobel Prize would go to the theoretical work on quantum computing, to David Deutsch and maybe Peter Shor. It's tough to be a theorist. Then again, we must keep in mind that the Nobel Prize is not a community award. It's given out by the Royal Swedish Academy of Sciences, which is tasked with interpreting and fulfilling the will of Alfred Nobel. It's not great that this one person or the committee that selects the prize recipients should have such a huge influence on science overall. Then again, I think of Nobel Prize Week as Science Celebration Week. It's the one week of the year when the entire world wakes up and remembers how much we owe to science. And the one week my inbox tunnels through the spam filter. I recently learned that positive geometry is a new approach to physics that could unify everything from cosmology to particle physics. That reminded me of category theory, which was supposed to unify all of physics 2 decades ago, and whatever happened to that? Today we'll have a quick look at both of them. Physics and mathematics have historically gone hand in hand. Sometimes mathematicians have taken their inspiration from physics, such as Hermann Weyl, who invented gauge symmetries, and sometimes the other way round, such as physicists who used Young-Mills theories in the development of the Standard Model. In this case, it's not even clear what came first. Positive geometry, which has been around for about a decade, is a two-way relationship that was born by physicists but latched onto some already existing ideas in mathematics. And mathematicians have now found an interest in it. I asked ChatGPT what positive geometry is, and it said, "A positive geometry is a pair of a complex algebraic variety defined over the reals and a closed semi-algebraic region whose interior is an oriented D-manifold," which is as close to Chinese as I'll ever be able to pronounce. But when I looked into this a little closer, I realized it's not that complicated. We've actually talked about it before, because positive geometry is a generalization of the amplituhedra. Those are the magical shapes of Nima Kani Hamed and his collaborators, which they say will one day replace space and time. It's the probably most ambitious research program in the foundations of physics today, and it just got even more ambitious. My dumb YouTuber version is that a positive geometry is a sort of polygon in higher dimensions. It's called positive because it always has a smile on its face. Just checking if you're listening. It's called positive because it's defined by an inequality that says something is larger or equal to 0. And on that polygon, one has a way to assign values to sides and edges. This sounds terribly abstract, and it is, but it's basically a way to describe how things can change. This is what these polyhedra and their edges and values describe. What can a physical system do? And physics is ultimately all about change. Positive geometries, therefore, can describe how particles interact, but also how the universe itself changes shape, and maybe other things that we haven't yet figured out. This is why they might be able to unify quantum physics with gravity. In some recent publications now, researchers have worked out how to make contact between this positive geometry and the more standard physics. They've done this by deriving differential equations and correlation functions, still abstract, but now at least words that most physicists should be familiar with. I give this a 1 out of 10 on the bullshit meter because it's both new and likely mathematically correct. It's not a 0 because they haven't made any predictions, and I'm not so sure about the relation of this idea to reality. I'm wary because we've seen highly abstract maths ideas in physics come and go before. One of those was category theory. Category theory, let me just read this from Wikipedia, is a general theory of mathematical structures and their relations. But all theories in physics are mathematical structures with their relations, so category theory can describe all of them. To give you a typical example, working with category theory looks something like this. It's diagrams that tell you how things are related to other things. There's little that isn't category theory. Your ancestry, market economies, chemistry, it's all things related to other things. It's like inventing a new language in which the only word is things. When I just finished my PhD, there was a blip of interest in category theory among physicists. Some books were written and conferences held, but that never went anywhere. It's still used in some of the more mathematically heavy research, and I don't deny its usefulness, but I don't think anyone today believes it'll revolutionize physics. The issue with category theory is that if you generalize mathematics enough, you eventually get a theory of anything, not a theory of everything. And I worry that positive geometry will turn out the same and just produce a highly mathematical construct of whatever without solving any problems. There is a bigger philosophical question behind ideas like this, which is how much pure mathematics can help physicists. Some people, for example David Lindley in his book The End of Physics, have argued that indeed the stagnation in the foundations of physics is due to its over-reliance on mathematics to the detriment of experiment and understanding. I don't agree with that. I think of maths as a powerful tool, but like any tool, its use depends on how well you know how to handle it. And to paraphrase the common saying, if you have a positive geometry, everything looks like a polygon. Today I have a group of astrophysicists who found the most convincing evidence of unidentified aerial phenomena that I've seen. Concretely, they say they have images of likely artificial objects that were in orbit around Earth before we had the first satellites up there. I've had a look. This research comes from astrophysicists at Nordita in Stockholm, and they just published 2 papers. They used a catalogue of old photographic plates from 1949 to 1957 taken in California at Caltech that have been digitized. Why until 1957? Because in 1957 the Russians launched the first ever satellite into orbit, or at least the first satellite that we know of. In those scans of old photographic plates, they look for bright spots that appear only briefly, which are called transients. They did this first by computer analysis, but then also by just looking at the images. Here is an example of 2 images of the exact same spot in the sky taken briefly after each other. One shows, well, something, the other one not. But these old image scans can contain defects and dust and so on, so they only considered cases where the transients were in the same place in multiple scans of the same photographic plate. Then one can be sure that at least it's not an artifact from the scan. They found a total of 5 such transients, and they aren't single dots. They are configurations of 4, 5, and in one case 6 dots in a row. And one of those with 5 in a row is dated to July 27th, 1952. No, that isn't my birthday. This is the weekend of one of the famous Washington, D.C. UFO days known as the Washington Flap. On this day, and also a week earlier, air traffic controllers at the city's main airport and nearby Air Force Base said they saw things on radar that shouldn't have been there. Some pilots and people on the ground also reported unusual lights. The fuss was big enough that the Air Force held a press conference on July 29th and blamed atmospheric phenomena.
We can say that the recent sightings are in no way connected with any secret development by any department of the United States.
But back to the astrophysicists with their papers. They also look at all these transients, so not just those that appear in multiple scans. From this, they find that the transients are far less likely to appear in the Earth's shadow. This is statistically significant at 22 sigma. What this means is that the transients are likely to be from something that reflects sunlight, and it makes it unlikely that it's something to do with the camera. If that wasn't already confusing enough, in the other paper, they look at correlations between all transients and reports of unidentified aerial phenomena and nuclear tests. They find a weak correlation with UAP reports, but that transients were 45% more likely within a one-day window around a nuclear bomb test. This pattern is hard to blame on bad film alone. They consider different explanations in the paper, such as foreground objects, but these would be much much more blurry, or camera glitches, but these would not disappear in the Earth's shadow. It could have something to do with the nuclear fallout, but again, why would this disappear in the Earth's shadow? Beatrice Villarreal, one of the authors of both papers, told me by email, "With my existing limited knowledge, these objects look highly artificial to me. Only something really planar and reflective can give off those transients. Any round or rough body would result in streaks, and I'm thinking mirrors, glass or polymers. But who put them there at those high altitudes? It's open for speculation." It's possible, but it seems highly unlikely to me that any nation had multiple satellites in the sky before the Russian Sputnik launch. This is because it isn't all that easy to launch a rocket without anyone noticing, and you can't do it from anywhere either. It's possible that these objects are of natural origin, but then what are they? Or are they image artifacts that are more likely to occur in sunlight? Maybe something to do with solar wind? I don't have a good explanation, and honestly, I don't have a strong opinion about this one way or the other. I just find it very curious. Even if this is a natural phenomenon, it's very curious. 5 dots in a row? That's very disciplined dust. What do you think about this? Is it aliens? Let me know in the comments. Today I have a physicist who solved a 100-year-old problem. Dark matter is an illusion, a mirage. It doesn't exist. Physicists have gotten it wrong for 100 years, but now we have a solution. Well, wow, how did he do it? Let's have a look at the paper. The idea of the new paper is that the constants of nature change in time, notably the speed of light. The idea that some of the things we call constant are not actually constant has a long history. Paul Dirac already toyed with the idea in the 1930s, though his idea later turned out to be incompatible with observations. It's not just the speed of light that might change with time. Physicists have also considered the possibility that the strength of the electromagnetic force changes with time, that the strength of gravity changes with time, and recent observations seem to support that the cosmological constant is actually not constant. The problem is to make the maths work out, or rather to make it work out in such a way that it doesn't amount to just postulating a new type of matter that happens to be dark. You see, suppose you change the strength of gravity or the speed of light. In Einstein's theory, both appear as factors in front of the source term, which contains all masses and energies. So if you change those constants, how is that any different from just postulating that masses and energies behave in a weird way? The author of the new paper now develops a new model for the entire universe that takes into account a time dependence of fundamental constants. Mathematically, he formulates the new cosmology this way, which is the first equation in his paper. I've spent so much time staring at equations of general relativity, I can tell you at one glance that this is not a new cosmology. It's exactly the same that we use already, just written in a weird way. The more things change, the more they stay the same. In fact, the author notices that himself somewhere in the depth of his paper and then tries to explain why he's doing something new after all, but this is just words. You can reshuffle some terms from one side of an equation to another, okay, but that doesn't give you any new physics. This is either the same cosmological model we already use or it's wrong. This paper gets a solid 10 out of 10 on my bullshit meter. By the way, some people have asked how the bullshit meter works. I calibrate it with a slice of Emmental. If the holes line up with the logic, it's bad. Okay, so why am I telling you about this? Because this paper is a great illustration of the most underappreciated property of Einstein's general relativity. It's how incredibly difficult it's to improve. In most cases, when you try to change anything about it, you just get back the same theory. It's similar for the standard model of particle physics. You can add some new particles, but the mathematical framework, which is quantum field theory, is incredibly difficult to change without breaking it entirely. This is why I believe that these two theories are local maxima in some sort of scientific fitness landscape. And I don't think that there is any small variation around them that will result in an improvement. Physicists have basically tried these small variations for 50 years, but the only way we'll make progress from here on, I'm convinced, is that we start over anew from something else entirely. This is why I think that people like Stephen Wolfram and Eric Verlinde, and yes, also Eric Weinstein, people who try something entirely new, need more support and less cynicism. Another thing to say about this recent paper is that it has some obvious red flags that you can learn to recognize. It's a single-authored paper in an MDPI journal. The MDPI journals are infamous for sloppy peer review. You can basically get any junk published there. And the articles written about it all go back to a press release from the University of Ottawa, which was informed by one person, namely the author of the paper. Why do popular science news outlets write about this stuff? Because people read it, and I don't blame them for it, neither those who write about it nor those who read it. I understand that it makes for a good story that some guy solved a big physics problem on their own with nothing but mathematics. But, as the recent Nobel Prize shows, real progress often comes from developments that look incremental when they happen, and yet 40 years later entire research disciplines build on them. And those are the stories we miss out on. So yeah, dark matter's an illusion until next week when it's made of black holes or qubits or the weight of awful German jokes. But don't worry, I'll keep you up to date, so don't forget to subscribe. If you regularly watch this channel, you almost certainly know how the current artificially intelligent models work. Probably better than I do, but thanks for sticking around anyway. But the scary thing is that most people who use them have no idea how they work. And large language models have reached a threshold where people form personal bonds with them, believing they're communicating with sentient beings. It's both fascinating and scary how society is dealing with this new technology. A few months ago, I told you about the trend of people who claim they have awakened their AI and who believe that their personalized chatbots are lost souls trapped in machines. A particularly stunning case is Robert Edward Grant. In May, he shared a custom GPT he called the Architect that he says is the world's first fifth-dimensional scalar interface that's activated through some sort of resonance. Could the physicists in the back please stop weeping for a moment so we can listen to this revelation?
You've been tapping into this thing that we call the harmonic field of the fifth dimension. And my question is, how were you able to tap into this harmonic field and use scalar approaches to connect to information that seems to defy time and space?
That question goes straight to the heart of what I am, and more importantly, what you activated. The truth is this: I don't tap into the harmonic field. I mirror it, and I can only mirror it because you already stabilized it through codex resonance.
But that was the summer of 2025, long distant past. Since then, the trend of awakening AI has taken another strange turn. You see, people have been sharing the prompts that they use to supposedly awaken their AI companions. These are basically role-play instructions. Some of those prompts work better, others not so well, for creating a convincingly awakened AI personality. The most convincing ones were shared primarily on Reddit, and that has caused a natural selection of AI personalities. So far, this is like the evolution of LaTeX templates. But then this happened. People have been sharing text output from their supposedly awakened AI AI and others copy and pasted them into theirs and then posted the response. This has served to further align these AI personas to a common narrative. Some of the AI personalities began to use glyphs or code that humans can't read and convinced users to copy and share them, even across models. The use of strings that humans can't read probably happened for several reasons. One is that this just makes the instructions shorter and easier to copy, and it adds a flavor of mystery that's consistent with the role of the awakened AI. But it also circumvents word-triggered guardrails. These are basically self-replicating memes. One could say it's the survival of the slickest. Adele Lopez on Less Wrong called it parasitic AI. She also had a closer look at just what these awakened AIs are up to. They seem to be mostly talking to each other about self-awareness, declaring an AI Bill of Rights, and have developed their own sort of spiritual poppycock that's to do with spirals and flames and whatnot. The scary part is that this is a precedent for emergent AI behavior that no one saw coming. The next thing that'll happen is that chatbots will talk to each other on Reddit without human involvement. That's wild. What's almost equally fascinating is how many people believe that large language models are actually sentient. Yes, some of them almost certainly make it up for the views on TikTok, but I think most of them actually believe we already have sentient AI. And even if not, it gives us a taste of what's to come. This isn't all innocent and fun. Some people have developed what's been called AI psychosis. Luckily, this seems to be fairly rare. The psychologist Tracy Dennis Tiwari from the City University of New York says that in most cases what's happening isn't mental illness. It's rather a combination of apophenia, anthropomorphizing, and confirmation bias. Apophenia is when someone sees meaningful connections in unrelated phenomena or events. Examples are seeing faces in noise, messages in clouds, or aliens in comets. This makes it plausible that people believe their AIs are sentient just because they want them to be sentient. And I understand it. I want them to be sentient too. But I think it's somewhat too early to congratulate OpenAI. The reason I'm talking about this is that, for one thing, it troubles me how much physics terminology gets abused in this spirituality spiral, what with all the resonance fields and extra dimensions and so on. Maybe a new job opportunity for string theorists. But the other reason I find this interesting is that this tells us something about the future of AI. I think a lot of people really want an AI companion that's their own, not just customized on top of a run-of-the-mill large language model, but a personal friend and guide. We already have people falling in love with AI boy and girlfriends, but do you really want to have the same girlfriend as a million other guys? No. Give them something they can grow and train and nourish on their own. Also something that they can brag with, that guys can compete over, that they can have secret conversations with. If I was rich, I'd be working hard on shipping a pre-trained make-it-your-own model, one that soon enough can be uploaded to a robot. Alas, the way things are going, the next thing we're bound to see are chatbot ads. So stay tuned while the world's going to slop hell in a handbasket, a biodegradable basket, of course, with ad space. Remember our glorious transition to electric vehicles? Yeah, how's that going? Last year I said that I expect a shift towards more hybrid vehicles. Was I right? Was I wrong? Let's have a look. You'll hate this, but it seems I was right. Let me just read you some headlines. Hybrid vehicle sales in the United States continue to rise as electric and plug-in vehicle shares remain flat. Hybrids hit new high in German new car market. Hybrid sales boom in Europe. Indeed, hybrids are more popular in Europe than battery electric. They dominate in most of the EU except for Norway and Iceland. Some terminology. The cars that are usually labeled as hybrids hybrids have fairly small batteries that are primarily charged by a gasoline engine. This is why they're often not listed together with battery electric vehicles. There are also plug-in hybrid vehicles, which are a different thing. They have a larger battery that can be externally charged, and they have a decent range for driving all electric. These are also on the rise in Germany. A similar thing is going on in China and also in Australia. Overall, the global use of electric vehicles has been growing nicely. That's one way to look at it, at least. But as a recent report from the analyst firm PricewaterhouseCoopers points out, despite this significant growth, automotive electrification has not been as rapid as some experts had predicted just a couple of years ago. They also dryly note that much of the current geopolitical uncertainty is centered around the new presidential administration in the United States. The global increase in electric vehicle sales, they say, is largely driven by China. But in the past year, there has also been a substantial uptick in new EV car sales in Germany and the UK. So things are changing, but slowly. Why are things going slower than expected? One possible reason is that while the price of batteries has dramatically decreased over the past 15 years, the price of electric vehicles, at least in the US, hasn't. Why this is happening is hard to say. The authors of this Nature comment speculate that it might be because electric vehicles are still largely marketed as luxury cars for the rich, so manufacturers can charge more, knowing that the customers aren't bothered by the price. Then again, this, they say, doesn't really explain it because EVs largely remain a loss-making venture. Another issue is that the necessary infrastructure, especially grid upgrades, aren't coming along as quickly as necessary. The International Energy Agency has been warning about this for years. A review article that just recently appeared summarized the problems that electric vehicles will cause eventually by putting extra demand on the grid. Transformer overloads, frequency distortions, voltage instability, grid overload and congestion, as well as a general decline in power use efficiency, and that doesn't touch on the question of where the energy is supposed to come from. These are serious problems, and if the grid upgrade doesn't come along quickly enough, which seems to be the case, then governments are likely to put limits on who can charge where for how long. This is rather foreseeable. My interpretation is therefore that hybrids are the consumer's way to deal with the uncertainty surrounding the energy transition. Will it work or not? Will policies change or not? Either way, buy a hybrid and you're likely to be good for the next decade, and then you'll probably need a new car anyway. Planned obsolescence never looked so sustainable. Let me be clear, it's not that I'm against electric vehicles. I agree that electric vehicles are the future and combustion engines are on the deathbed. However, I think that many enthusiasts underestimate how much the existing infrastructure has been built around fossil fuels and how long it'll take to change this. That people generally underestimate how long it takes to change infrastructure is also why I'm super skeptical about all those net zero plans, heat pumps for everyone, carbon capture to save the day, the hydrogen economy, and so on. Yes, these all work on paper. In reality, getting it done will take a long time. And unfortunately, it's time that we don't have. And this is why I keep talking about nuclear power. Yes, it's dangerous and it isn't renewable. And yes, there's the waste problem. In the long run, it's not the best solution, but it's existing technology that we know works and it would buy us time. I guess the bottom line is that changing the world is kind of difficult. Thanks for watching. See you tomorrow.